Before we embark on the details of this chapter related to circular motion, let's understand some simple terms related to the kinematics of circular motion. The simplest term that you must understand is angular displacement. Take a look at this ball here. It's rotating like this. Let us say it rotates an angle delta theta. This radius of the circle in which this ball is rotating is r. In that case, let the length of the arc rotated by this ball be delta s when the angle rotated by this ball is delta theta. This angle is measured with respect to the initial starting line from which this ball starts rotating. In this case, delta theta is termed as the angular displacement of the ball. Understood? So if any body is moving in a circle, then the net angle made by that ball or that body in that instant with the initial radius vector is called delta theta. So for example, if this ball rotates by 50 degrees, from the initial radius vector, in that case its angular displacement is 50 degrees. If it rotates by pi radians, you can say that the angular displacement is pi radians. Now we know that the arc of a circle and the angle subtended by the arc at the center of the circle are related by the equation delta theta equal to delta s by r. So the angular displacement is equal to the linear displacement divided by the radius of the circle. You see, delta s is the linear displacement of the ball. The interesting thing here is that the angular displacement is actually a vector quantity. That's interesting, but this is true. In fact, you must remember that the delta theta vector, the angular displacement vector, is actually equal to the delta s vector divided by r into r unit vector. We have multiplied our equation with r unit vector here because the direction of the angular displacement vector is such that it is along the cross product of the radius vector and the delta s vector. Understood? So right here, for example, the radius vector points towards the right, isn't it? The delta s vector, on the other hand, curves upwards. We know that in case of a cross product, the cross product vector points in the direction of the thumb. If you curl your fingers from one vector of the cross product to the other vector of the cross product. So in this case, if you curl your fingers from r unit vector to delta s vector, the thumb points in the direction of the angular displacement vector. In this case, if you curl your fingers from r to delta s like this, you will see that the thumb points upwards, that is perpendicular to the plane of the paper, outwards, isn't it? This angular displacement, this direction of the thumb, represents the direction of the angular displacement vector. So you must remember that delta theta is equal to r unit vector into delta s vector divided by r. Understood? This is the vector expression for the angular displacement. It is there in the direction perpendicular to the plane of paper, such that when you rotate your fingers from the radius vector along the linear displacement vector or delta s vector, the thumb points in the direction of the angular displacement vector. So this is something you must remember. As you may already know, the angular displacement vector is measured in radians in general. Sometimes it is also measured in degrees. Let's now discuss another interesting concept, the average angular velocity. Let us say a ball is rotating in a circle. In that case, the net angular displacement of the ball in a given time is called the average angular velocity of the ball. Understood? The average angular velocity is represented by this symbol omega. Omega is delta theta by delta t. As you can see, if the ball rotates by an angle 20 radians and it does so in 10 seconds, then the average angular velocity will be 20 by 10, that is 2 radians per second. Understood? This is quite simple. Basically, it represents the rate of change of angular displacement. Just as velocity is the rate of change of displacement, average angular velocity is the average rate of change of angular displacement. It is equal to total displacement divided by total time. It is measured in radians per second. It is also a vector quantity. As you can see, omega vector is delta theta vector by delta t. What will the direction of the omega vector be? The direction of the omega vector will be along the direction of the change in angular displacement. So you can again curl your fingers along delta s unit vector, and the thumb will tell you the direction of omega. In most of the cases, the direction of the average angular velocity is along the angular displacement. Another important topic is instantaneous angular velocity. Just as in the case of instantaneous velocity, which we studied about some chapters ago, instantaneous angular velocity represents the rate of change of angular displacement at any particular instant. So let's say this ball is moving, an angle delta theta in time delta t. Then its average angular velocity will be delta theta by delta t. However, in between the path, the ball might have moved a small tiny angular displacement d theta in a small tiny time dt. Similarly, if you consider another point on its path, the ball might have moved a small angle d theta as it went from this point to this point in a small time interval dt. So basically, the rate of change of angular displacement might have changed along the path. Delta theta by delta t gives us the average angular velocity. But what is the angular velocity at every instant? What is the rate of change of angular velocity at any instant if you consider a very small time interval dt, in between the motion of the particle?